So what we want to do here is essentially use the derivative as a rate of change. And we're going to check how the rate of change from something can be put in terms of the rate of change for another thing. Okay? When we're checking rate problems, we need to read the problem carefully. These are applications, so we need to be careful and define some sort of sketch of the situation that we're given and identify the rates that are going to work in our problem and find which of the rates is going to be determined, which of the things is need to be determined and what are the things that are given. Then we need to write one or more equations that are going to express the relationship among the variables, introduce rate of change by differentiating the appropriate equation with respect to time. And you can say, why with respect to time? Because we're talking about rate of change of elements with respect to time most of times. Then after that, we're going to substitute the known values in our rate of change, and we're going to solve for the desired quantity. Then after that, we're going to check that the units are consistent and if the answer is reasonable. So for example, does it have the correct sign? Check things like the velocity has units of velocity, so distance over time, and that kind of thing. But let's see this with examples because there's no other way to theorize about rate of change. So first, we have an example of converging planes. We're going to have that two planes are coming from the airport here. One is going to be flying to the west at 120 miles per hour. So you can see the plane flying from west to the airport. And the other one is flying north. The first plane is flying at 120 miles per hour. Notice that this is the rate of change. This is the rate of change of distance over time, or you can say that is the speed. Okay. The other one is also having a speed rate of change, 150 miles per hour. This is the rate of change of distance over time. So again, the speed. We're going to assume that they fly at the same constant elevation. So how fast is the distance between the plane changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport? So notice that at this point, we have a ton of information. We have information about the speed and we have information about when we want to check the distance. We want to check the distance with one of them is at 180 miles from the airport and the other one 225 miles. Then what we need to do is we need to set up the information that we know. Okay. So first thing, let's check the rate of change. So we have the rate of change of x. So we're calling this distance from the westbound plane, we're call it x. We call y the distance from the northbound plane. So the x dt and the y dt are the respective speeds, okay? Because they're going against the positive direction, this is going up and this is going to the left, we're saying that they're both negative rate of change. So this will be negative rate of change of x minus 120 miles per hour. Notice this is first value. The rate of change of x with respect to t. Then the rate of change of y with respect to t is minus 150 miles per hour. Now, with that, we have information on the rate of change. But we can also get a lot of information from just the setup. We want to know what is c, okay? And so to get c, we're going to use a little bit of the relationship of the relationship by the triangle that is given. So let me just pull the board over here. So we're going to have that this is the airport, and we have this is x, and this is y, and we have this distance being c. Okay, and here are the plane 1 and the plane 2. Now, by the relationship of the Pythagorean theorem, we have that this is a right triangle, and c squared is equals x squared plus y squared. Now, we have a lot of information on rate of change, right? So we can probably calculate the rate of change of the distance between them, and we can do that by taking the derivative. So we're going to assume that all these functions are functions of t. Okay? That way we can make everything vary with respect to time. Then if we take derivatives, this is an implicit derivative, and we have 2c times the c dt is equals to x times dx dt. Notice that I'm doing chain rule here, and 2y the y dt. Notice that we do have some information that we can use. We can use information about the rate of change. So we know the x dt, this is given, and we know the y dt, that's also given. We know that the y dt is minus 150 miles per hour, and we know that the x dt was 120, right? Plus, we care about specific moments. We care about when x is 180, and we care about when y is 225. So we can assume those values. We care x 180, y 225. Okay? So those are the values that I have right now. First, from this, we can get the value of c. Notice that since c squared is x squared plus y squared, then c is just going to be the square root of 180 squared plus 225 squared. Okay? And so from there is that we obtain that c is 172.9. Okay? Now, in the same fashion, now that we got x, y, and c, and we have the x, the y, and the t, then we can plug the values in here, and we're going to get the value that we need, that is the c dt. Notice this is twice 172.9 times the c dt equals 2 times, and so x is 180, and the x dt is minus 120, and this is, notice that this is miles, and this is miles per hour, and this is also over here miles. Okay, and so plus 2 times 225, and then minus 150 miles per hour, and this is miles as well. So at this point, I can divide by the 122. So notice that this is going to be 180 times minus 120 divided 172.9. The 2 is going to get lost with the 2. And now notice that the miles is going to get lost with one of the miles. So we're only going to get miles per hour once that we divide with this miles here. Plus, and we get 225 times minus 150 miles per hour divided by 172.9. And so now this is the final value, and we're going to get that this is actually minus 192.1 miles per hour. Okay? So as you notice, we do a lot of basic arrangement before we actually get to the rate of change. We first need to establish a function that is going to be what we need to find. Notice that we always find in the distance between the planes, which is c, and we want to check what is the rate of change of that distance. How fast is changing? How fast is the distance between the plane changing? So we need to express that in a function. Then we need to differentiate and then check how the rates are related. Okay? And here you can see what I did in the board, essentially taking the derivative of all these values, and essentially getting the dc/dt. Now let's go for the second example. In this second example, we're going to have a cone for coffee. Okay? So coffee is draining out of a conical filter at a rate of 2.25 inches cubed by minute. If the cone is 5 inches tall and has a radius of 2 inches, so how fast is the coffee level dropping when the coffee is 3 inches deep? Notice that this has a lot of setup. And here we have the paper cone, for the paper filter, which has a cone shape. And we have the coffee inside that is a different level. And then as dropping coffee. So this is losing altitude in the terms of coffee. Now the full conical filter is 5 inches and it has a radius of 2 inches. Okay? But the coffee, we don't know. We don't know the relationship between the coffee. We have that the coffee has certain radius and it has certain height. And if we have the information about the volume of the cone, we can talk about the volume being 1/3 of pi r squared h. So with this, we can kind of discuss the volume of both the cone and the coffee. Now, the relationship that we get here is going to need to be put in a single variable, similarly to the case when we are optimizing. So what's going to happen is that we're going to set up this piece of the cone, and we're going to look at this as two triangles. One of them with altitude 5 and base 2, and the other one with altitude h and base r. So because they're both right triangles, there's a similarity, and I can create a ratio between them. And having the ratio of r between h is going to be the same thing that having the ratio between 2 and 5. Those things are called proportions. Okay? We're going to use that a lot when we're dealing with volumes and trigonometric relationship and triangle relationships. Now, because we can establish this relationship here, we can put the radius in terms of the height or the height in terms of the radius. Then, with that, notice that putting the radius in terms of h, I can just put that in the volume equation, and I can get a volume equation that now is only in terms of h. So the volume in terms of only h is going to become 4 pi over 75 h cubed. Notice that this is only for this case. Now, we can do what we always do. We can take the derivative here with respect to the time, and we're going to assume that everything is varying with respect to the time. And so the rate of change of the volume with respect to the time is 4 pi over 25 h squared times the derivative of h with respect to dt. So the rate of change of the height with respect to time. Okay, so from here, we jump to here. Notice that at this point, we have our related rates equation. Of course, we do know about the speed that the height is draining, right? So notice that the coffee is draining out of the conical filter at a rate of 2.25 inches cube per minute. So that's going to give us the information that we have with respect to volume. So we don't know the altitude here, and that's what we want to check. So, but since we know the information about the volume, we can just solve for the rate of change of the altitude in terms of the volume, and then we plug the values. Notice that we're plugging with h is equals 3 in deep, and we change the rate of change of the volume. Notice that this is inches cube, and with inches square is going to get canceled 2 inches, and the minute is going to remain. So we're going to get here that this is going to be minus 0.97 inches per minute. And so that's going to be how the height changes with respect the time. We can see that in 2 different ways. In terms of graphical points of view, we can change how the radius and the height are changing with respect to time. Notice that we can actually get the information from the radius with this information here. We can calculate the RDT, and it's going to be 2/5 the HDT. And so that will give us this rate of change in case we want to. And that's going to tell us how fast the radius is actually going. On the other hand, we just obtain how the height is varying with respect to time, and finally how the volume is going with respect to time was given in the initial assessment. So we have first the full volume, and then this slowly is going to go until it reaches 0,